Hey everyone, we're going to start taking a look at electric fields. To introduce the concept, we're going to take a look at something a little more familiar, gravity. If we look at a picture of the Earth, if you were to take an object with a mass m and have it above the Earth, we know that the Earth is going to pull that object down. There's going to be a force exerted on the object, we call it the force of gravity, and it's going to pull that object towards the center of the Earth. Doesn't matter where on Earth you have this object, if you hold it and you let it go, it's going to be pulled towards the center of the Earth. Now, if that object was placed further away from the Earth, like way out here, the force is still going to be pointed towards the center of the Earth, but as we've learned in previous units, the force decreases in strength the further you get away from Earth. That's because force of gravity, remember, was big G m1, m2 over r squared. The bigger r gets, the weaker that attraction is, that force of gravity will be. But it's always pointed tangent towards the center of the Earth. Same thing is going to be true for charges. If we have a big charge Q here, let's call it, let's make it a negative charge. If you put a tiny little positive charge, we call it a test charge, nearby, since it's attracted to the negative sign, it's going to have a force pointing it towards Q. We call it the electric force instead of the gravitational force. Similarly, if you put that charge, that test charge, further away, it's going to have a smaller electric force. Because as we learned with Coulomb's law, the electric force is K Q1 Q2 over r squared. The further that r gets, the distance between the charges, the weaker that force becomes. The electric force and the gravitational force are called field forces, meaning the charges and the objects don't have to be touching to exert forces, to push or pull on each other. It's not like friction or normal or tension where things have to be touching to push or pull. Gravity and electric force are field forces. So we need to be able to see, visualize this field around the Earth or around this charge. So around the Earth, let's do this in green, you can imagine that there's these lines, these invisible imaginary lines pointing inward towards the center of the Earth. They represent the gravitational field around the Earth. These lines kind of give you an idea of, if you let go an object, what direction is that object going to get pulled? And it's going to be tangent to those green field lines. Okay, they're a made-up concept that helps us visualize what's going to happen when you put an object in that field. Same thing around this charge. The electric field lines are going to point towards this big negative charge, radially inward. And so if you drop this test charge in the field, the green field lines here kind of give you an idea what direction that charge is going to get pushed or pulled. Now, there are some rules for drawing field lines. Let's get into those now, and then we'll go over some examples of each. So don't get overwhelmed with seeing these rules. There's 5 of them. I'll explain each one as we go. So rules for drawing electric field lines. Sorry for my penmanship. Rule number 1. Field lines are going to be drawn radially outward from positive charges into negative charges, or infinity, as you will see. For example, we have 2 charges on the screen here. We have 2 particles on the screen here. Neither one has a charge right now. But if I give a positive 1 charge to the particle on the left, you can see the field lines are generated here. They're pointing radially outward, away from the positive charge. And they can go into infinity. That's totally fine. If I make the particle on the right a negative charge, like a negative 1, you can see some of the field lines from the positive go into the negative. Okay, so it's okay for field lines to either go out from positive to negative or out from positive into infinity. The opposite is true for the blue negative charge. Field lines come in radially from a positive or from infinity. So field lines go out from positive and into negative. Rule number 2, field lines never cross. You can see that in this image here. The field lines between these two charged particles never crisscross each other. Rule number 3, the number of field lines either into or out of a charge is proportional to that charge. So let's go back to just having one charged object here. We've got our +1. If I make this red charge a +2, we get double the number of field lines. If I make it a +3, we've got 3 times the number of field lines, 4 times the number of field lines, and 5 times the number of field lines. The bigger the charge, the more field lines you would draw. Rule number 4, the direction of the electric force, either push or pull, either attraction or repulsion, the direction of that force at a point in the field is directed tangent to the field line at that point. Okay, so let's take a look at that. All right, we're using a different simulation here. I've got a positive charge and it's creating a field. The brighter the line, the field line is, the stronger the field is at that point. If I grab a yellow sensor, the sensor acts like a little positive charge, and it will give you an indication with a red arrow here of what direction that positive charge is getting pushed. So obviously, if our charge here in the middle of the screen is a positive, the test charge is going to get pushed away, like charges repel. Okay. If I put it at a different location, notice the arrow has changed its direction to always be tangent to these field lines. Okay. Always tangent to those field lines. Even if we add another charge in here, like a negative charge here, so now our field is going away from the positive and into the negative. If I bring in a positive test charge, okay, the force that charge is feeling is still tangent to the field lines here. So if I follow it all the way around in this field, you can see that anytime I'm on a field line here, you can see the direction is always tangent to the field lines. And since the yellow sensor here is a positive charge, it's going towards the negative, away from the positive. Our 5th rule here is that the closer the field lines are to each other, the stronger the field and therefore the force will be at that point. The closer the field lines are, the stronger the field is. So the further apart, on the opposite direction of this, the further apart the field lines are, the weaker the force and field will be at that point. Going back to this simulation, if I take my yellow positive sensor and I put it where the field lines are going to be really close, you can see the big red arrow here has a big force pointing towards that negative charge and away from the positive charge. The field lines right in between the charges are going to be really, really close together. So you get really big forces where the field lines are close together. If you go way out in space where your field lines would be spreading further apart, I know in the simulation they're just dimmer, but if you were drawing these field lines yourself, these lines would be further apart from each other. So the force gets much, much weaker the further the field lines are from each other. The closer you get to the charges, the bigger that force becomes. Further away out in space where there's no field lines, the weaker the force becomes. So let's take a look at an example here. I've got 2 charges shown on the screen, and we've got field lines coming out of one and into the other. So first of all, our red charge must be a positive value because the field lines are coming out of it, and our blue charge must be a negative value because it has field lines going into it. Second thing you can figure out is their relative charge. So right now, if you count the field lines going into the blue charge, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 field lines going into the blue negative charge. Whereas for red, there are approximately double, roughly 18. I think there might be 20 actually in this picture, but it's roughly double, which tells you that the charge of your positive value is about double the blue. So it could be a +2 and a -1, or +4 and a -2. We can tell the relative charge. So if we made blue -1, that would make red +2. Next example here, we've got 2 charges that both appear to be positive because field lines are coming out of each other. And you can see that their field lines are interacting in such a way that it kind of shows them repelling each other because they're both positive and like charges repel. So you can see you kind of form these vertical asymptotes in between the 2 charges, showing that they are, in fact, repelling each other. So if we were to, let's say, plant a little positive charge somewhere, let's say right here, a tiny little positive charge, it's going to get pushed tangent to those field lines. So if there was a field line right at that point, it would be pointed vertically upward. That would be the direction that the force is on that tiny little positive charge. If we drew that same positive charge out in space here, where the field lines are much further apart, that force is going to, again, still be tangent to where a line would be through that point, but it's going to be a much weaker force compared to the first one we drew. If we drew an electron somewhere, like let's say that our electron is here, it's a negative charge, now it's going to be attracted to the positive charges that we have on the screen. So the force is going to be tangent to the field lines, but towards this closer positive. And it's going to be a nice big force because the field lines are pretty darn close at that point. Next example, looks like we've got the same number of field lines out of our red charge and into our blue charge, so that makes this like a positive 1 and this like a minus 1. We've got our field lines shown. If we put a little positive charge, let's say up at this point here in space, if there was a field line going through that point, which we don't have one, but if we drew one, it would look like this dashed line that I've just created on the screen. So our force on that particle is going to be directed tangent to the curve, and since our charge is positive, it's going to be going away from the big red positive charge and towards the blue positive or blue negative charge. So tangent to the line, there's our force. If we were to have put, let's say, a negative charge at this point here, the force on that charge again would be tangent to a field line at that point, but it's going to be going away from the negative because likes repel. And the field lines here are much closer than our last example, so we're going to have a much larger force pointed tangent to the field lines. Last example now. We've got a row of positive charges, a row of negative charges. If I just wanted to draw the electric field between these two rows of charges, neglecting everything outside of between them, I would have field lines going from positive towards negative. If I were to take let's say an electron, and fire it into this space in between these two rows of particles, these rows of charged particles, we're launching this electron into the field. That electron is going to feel a push. Okay? The electron is going to be attracted to the positives and repelled by the negatives. So the force that this electron is going to feel is going to be tangent to these field lines that we just drew on the screen. So if I drew the force in, let's say, orange, the force is going to be upward on this electron as it makes its way through the electric field. What's going to happen is this electron has momentum, so its path is just going to get curved. What direction is its path going to be curved? It's going to be curved upward because the force, all these orange forces are pushing upward. So our electron goes into the field perpendicularly, but it's going to have its path curved, and it'll come out of the field going in a different direction. This is the basic principle behind a particle accelerator like the one in Batavia at Fermilab. You've got this giant circle underground, and to accelerate particles to near the speed of light, you can't just have a launcher that shoots these particles and causes them to miraculously go in a circle. You have to shoot the particles in a straight line. There's usually an acceleration ramp or an acceleration loop. You shoot the particles along that loop, and then they enter the loop, and then there's going to be these charged walls all the way along the track that are going to have positive and negative sides to them, positive and negative sides, that are going to cause there to be a force on these charged particles, and that force causes them to bend their path, and these particles follow a circular path all the way around the loop. And so they never touch the walls, they never collide, and you can cause particles to go in a circular path without ever having to touch them by using the field force. If you would like to play around with the simulations that I've shown you on the screen here, charges and fields, that will bring you to one of them, and then this other link here will bring you to the others, so you can kind of mess around for yourself and see how the fields will look. Hopefully this helps you with your homework.